So today, we're gonna start our discussion on transformation of stress and strain. So this is gonna be a like as making a foundation of combining all the loadings, because after learning how to transform the stress and strain, then we can somehow mix up the normal stress and shear stress contribution from different reaction force and torque. Then we can have some sort of a foundation for analyzing complex and mixed loading structure problems. Okay, so let me give you a graphical highlight of this new chapter. So I think most of you would remember. So when we learn about the actual loading in the chapter 2, we have this simple actual tension loading. So if you take x and y coordinate in this way, it's purely normal stress state. There is only non-zero sigma x and tau xy and sigma y is 0 if we consider xy coordinate system. However, for the exactly same loading, instead of xy coordinate, if you take d coordinate or e coordinate, or to be consistent with your general calculus course, if you take x prime y prime axis, even though we are considering exactly same stress state, with respect to x prime y prime coordinate system, we're gonna have mixed normal stress and mixed shear stress state. Okay, so even though the identity some quantity is identical, I mean here the quantity means stress state is identical depending on our viewpoint, or in other words depending on our coordinate system, its reading can be different. Okay, and same thing also can be seen in our pure torsion problem in chapter 3. So for this pure torsion problem in chapter 3, if we take x and y coordinate system in this way, we don't have any normal stress component, and we have pure shear stress here. However, instead of taking xy coordinate, if you take this as x prime, this as y prime coordinate, we can convert this into purely normal stress state, like a maximum tensile stress along x prime, maximum compressive stress along y prime, and no shearing stress if we take x prime y prime axis like a 45-degree angle from the original coordinate system. If we take x prime y prime system in different angle, we're gonna have a mixed normal stress and shearing stress state. Okay, so and as I told you, stress is not a vector quantity, and strain is not a vector quantity. They are tensor quantity. So for tensor quantity, we can find the analytical equation. However, it's not easy to memorize the analytical equation, so we use a special graphical technique to memorize the equation, and it is called the Morse circle. Okay, so we're gonna have a Morse circle to memorize the tensor transformation equation. And today we will learn about how to derive a Morse circle and how to use this Morse circle to find the stress and strain transformation. So let me make a comparison with your general your freshman calculus class. Back in freshman calculus class and back in freshman physics class, you learn about transformation of a vector. Okay, suppose that you have a vector, this red f. Okay, so this vector, has this kind of quantity. The magnitude is 5, and its direction is pointing in this direction. So in describing this arrow, the graphical representation of this vector, we can have two different views. Okay, first view we can have is xy coordinate system, or to describe the same vector we can choose different viewpoint, which is x prime y prime coordinate system. So if you take x and y prime system, this vector coordinate can be written as 4 and 3. Okay, so you have 4 in x and 3 in y, and 4 and 3 will be a coordinate of f with respect to xy coordinate system. However, if you take x prime and y prime as the coordinate system, then its coordinate will be 5 and 0. Okay, along the x prime, its length is 5. Along the y prime, zero projection of f. Okay, so what this guy indicate is that even though we are describing exactly same quantity, a vector f, depending on the coordinate system, our reading can be different. And we can imagine similar thing, for the exactly same stress state. So for tensor quantity, instead of one arrow, we use this this kind of notation. Okay, so for exactly same tensor stress state, depending on x y coordinate system, or depending on x prime y prime coordinate system, the reading can be different. Sigma x, sigma y, sigma z, and sigma x prime, sigma y prime, sigma z prime, and different the shearing stress reading. This reading can be different. But please remember that even though our reading is different, we're gonna describe exactly same stress state. Okay, so please find the analogy between freshman calculus class. So what are today's topic? Today's topic is two. So first we'll discuss about why do we need stress transformation in slightly better detail. After that, we'll try to do our example of transformation of plane stress problem, and we'll also derive a Moore circle and try to understand how we can use Moore circle problem. Okay, so let's begin from the first question. Why do we need stress transformation? The reason is very simple. First, as I told you, we want to somehow combine and find the maximum normal stress and maximum shear stress plane. Okay, so we want to find maximum normal stress, we want to find maximum shearing stress plane, because after predicting the plane with the maximum normal stress and plane with the maximum shear stress, we can also predict the maximum normal stress and maximum shear stress by comparing this with material property, normal stress, normal strength, and shear strength. Then we can predict the failure, and when predicting the failure, we can also predict at which plane the failure would occur. Okay, so one of the and please also remember that we want to predict failure also in mixed loading. So one of the quite famous example you might remember is the torsion of chalk. Okay, when you try to make a torsion of the chalk, the plane of fracture occurs in 45-degree angle to the long axis, and actually this 45-degree angle is the plane with the maximum normal stress, and the failure occur along this guy because this is brittle material. Brittle material fails on maximum normal stress, and ductile material such as polymer and rubber fails on maximum shear stress. So by obtaining the maximum normal stress and maximum shear stress, and the plane at which this stress value occurs, we can predict the failure of materials. Okay, so this is why do we need stress transformation. Okay, so with this, let me finish the recording of this first video of today's lecture.